Everyone knows the rule. Don't sputter etch metal oxides and try and look at high resolution XPS and the surface chemistry because ion beams change the chemistry. But what if that chemical change is exactly what we want? We took a series of cerium and molybdenum mixed oxides with various compositions and phases as determined by XRD and Raman, and we applied an argon ion beam. What we saw was the response in terms of the reduction chemistry was dependent on the composition of the oxide in play. Combining molybdenum with cerium in a mixed oxide stabilized those molybdenum centers against ion beam reduction. But okay, cerium is highly redox active and you potentially have to separate radiative reduction as well. Fine. What about some nickel and cobalt MoO4 oxides? Crystalline materials? Where addition of the first transition metals not only stabilizes the molybdenum centers against reduction, but the degree to which it does so correlates with bond strength. So why is this useful? Well, we also looked at a series of cerium titanates, where we rapidly lost chemical information as we changed composition. These materials became amorphous, XRD and Raman could no longer provide any insights. In fact, the only information that we could obtain on the formation of a genuine mixed oxide was from NEXAF's analysis at the B07B branch beamline and diamond light source. Once again, this method revealed a trend in response to ion beam exposure that enabled us to use this as an informative tool to better understand our materials. So the takeaway is simple. Ion beam damage doesn't have to just be an artifact. Used deliberately, it can actually be an informative probe. And this actually applies to radiative beam damage as well. So I just want to thank all of the co-authors and those contributing to this manuscript and our funders at the EPSRC and UCL Maps department.